Assalamu alaikum wa rahmatullah. We're back with another video lesson. In the previous lesson, we talked about Newton's second law in rotational motion. And do you remember what was Newton's second law in rotational motion? It was net torque equal to moment of inertia multiplied or times or just come on, what else could be? Dot product, yeah? No, that's a different story. So Newton's second law of motion, of course, equal to the net torque equal to moment of inertia multiplied by the angular acceleration. We've said that in translational motion, force equal to mass times acceleration. In circular motion, centripetal force equal to mass times centripetal acceleration. In rotational motion, Newton's second law of motion is called the net torque, where the torque equals to what? Equals to the moment of inertia multiplied by the angular acceleration. Of course, we said it could be clockwise or counterclockwise. If it is clockwise, it is negative. If it is counterclockwise, it is positive. Of course, it could be the angular acceleration could be increasing or decreasing. Of course, if it is increasing, that would be positive. If it is decreasing, it will be negative. We're going to use Newton's second law of motion, or net torque, in rotational motion. Torque equals to moment of inertia multiplied by the angular acceleration. V, angular velocity, acceleration, tangential acceleration, let's say delta t, these informations or these values were given. Now, if you remember, we paused at question 2 here, all right? We solved a lot of questions, of course. If not, please go back to the previous video lesson to understand this from the beginning. Okay, so now in this question here, it says a bicycle tire of radius 0.33 meter, that is the radius of the bicycle tire, with a mass of 1.5 kilogram rotating at 98.7 radian per second. That means it is what? It is angular speed, but whether if it is initial or final, you don't need, yeah? I mean, it's not like you don't need, no. You need to read the entire question so that you know what it is. What torque is necessary to stop the tire, right? To stop the tire, that means omega final will be 0, and then this one is going to be omega initial. All right, in 2 seconds, so delta t is 2 seconds, consider the tire as a ring. Why is the question telling us about this? Whenever it tells you consider the tire as a ring, that means you have to use the moment of inertia of a ring to calculate or to answer this question. So let's begin with this. Okay, so we have, or perhaps we can, let's get a rectangle. All right, so take a look. These are, let's see, what are the informations given? That's your first key. You have to write down what is given first, and then based on that, you can, of course, answer the question. So we have a tire. It says consider the tire as a ring. So the moment of inertia for a ring, you know that. For a ring, that will be equal to, let me erase this. Why did it take so long? All right, so ring equals to what? Equals to mr squared. Very good. Now keep this in mind because you will need this. It says the radius is, now we can write the information. The radius is 0.33 meter. Excellent. The mass is 1.5 kilogram. All right, what else? And it says is rotating at 98.7. We said this is omega initial, which is 98, as a matter of fact, 98.7. 98.7, that is radian per second. Omega initial. What torque necessary to stop? That means omega final is 0. What torque needs we need the torque, yeah? But what about the time? Before going to find this, it says in 2 seconds. So that means delta t is going to be 2 seconds, yeah? So what torque? So find the torque, yes? Or let's just say torque, yeah? So we can say the torque, based on the information that is given, equals to what? The torque equal to, or you can say the net torque here, equals to what? Equals to moment of inertia multiplied by the angular acceleration, don't forget. Okay, but by the way, I can find the angular acceleration first, then of course I can plug into the equation. If not, I can answer all this in one step. All right, let's just do this. So net torque, we can say Moment of inertia for a ring, remember, that is mass times radius squared. Okay, you can use small r, that is also fine, multiplied by the angular acceleration. You already know that angular acceleration equals to final minus initial, omega of course, divided by delta t. Now, do you see your way out? I hope so. All right, so mass, that is, it was 1.5, right, multiplied by the radius. What was the radius? 0.33. Don't forget, this is squared, okay? Only the radius squared, not the mass. And then multiplied by omega final, it is 0 because we're going to stop it. Initial is 98.7 in a time of 2 seconds, all right? Let's erase this. And, okay, I didn't want to erase this. 0.7, and then the whole thing, you can close the bracket. I think I should rewrite this one too because it seems a little bit confusing. Here's 2. So, use a calculator and tell me what is the answer, yeah? By the way, you're going to get a net or negative net torque. Why negative net torque? Because you're going to stop it, yeah? That means the tire is going to, or the, yes, the wheel is going to slow down. So let me do it. So 1.5 multiplied by 0.33 squared, only the radius squared, don't forget. I think I didn't get it. 1.5 multiplied by 0.33 squared. Okay, that is basically 0.16 multiplied by, let's open a bracket. We can just use negative 98.7 divided by 2. And of course, we'll get negative 8.06. If we're going to use 2 digits, of course, it is going to be negative 8.1 by rounding. And that is the, you can say the net torque, yeah? In this case, of course, is going to be Newton meter. So what is this negative for? This negative, it just means it is slowing down. Negative 8.1. Okay, and of course, that is negative 8.1. Now, we have another question in the section review, physics in action. It says what? A bicyclist exerts a constant force of 14 Newton, all right, on a pedal, let's say on a pedal, which is 0.15 meter from the axis of rotation of a bicycle wheel with a radius of 50 centimeters. If his speed is 2.25 meter per second, 3.0 second or 3 seconds after he starts from rest. These are keywords, guys. So what is the moment of inertia of the wheel? Moment of inertia of the wheel. Don't forget this. Now, let's do this question as well because it is very interesting. Perhaps I can redraw this, or maybe I can show you what exactly we're doing here. So let's change the background here. Okay, so stay with me. Now, let me use this. Take a look on this bicycle wheel, by the way. So here's the pedal. All right, take a look. Here's the pedal. Here's a distance to the axis of rotation. So there's a force, there is a distance, of course, and of course there's the radius of the wheel as well. So there are 2 different radiuses, guys. Don't forget this. Where you can consider this distance, this force, and the distance, of course, it causes a turning effect, and as a result, the wheel is going to rotate. Okay. So the information you need to write down is this. We are using constant force, so the force we're going to use is 14 Newton, okay? On a pedal, the distance of the pedal, or you can call it the radius, 0.15 meter. That is what, from the axis of rotation, that is going to be this distance right here, okay? And then perhaps I can redraw this, yeah? So here's this, let's say this is the pedal, okay? So this is the force where you're going to use, that is 14 Newton. Okay, and then this distance is going to be 0.15 meter. And of course, the radius of the wheel is 50 centimeter, which is 0.5 meter. Okay, so the next thing is, okay, axis of rotation of the bicycle wheel. It is a wheel, so that is for moment of inertia, don't forget. With a radius of, so we can say the radius of the wheel is 50 centimeter. We can just say 0.5 meter, don't forget this. if not 50 centimeter, divide by 100. If his speed is, so we have a speed, it says after he starts from rest. After he starts from rest, that means omega, or not omega, because this is tangential, or you could just say yes. So the speed is, okay, let's say V initial is 0, V final is 2.25 meter per second. That's, you can call it tangential. What else? In time of delta t is 3 seconds. What is the time? 3 seconds. Okay. What is the moment of inertia of the wheel? Okay. Disregard friction and moment of inertia of the other wheel, so we ignore the other. Okay, so take a look here. We're going to write the equation that we have. So we know that the torque or net torque equal to moment of inertia multiplied by the angular acceleration, correct? Yes. Okay, or it can remove the cross. I can just say moment of inertia multiplied by the angular momentum. Take a look. We don't have angular momentum, but we have something else, yeah? We have V final, V initial, delta t. Remember, we're going to use all this to find what? To find tangential acceleration. Divide by radius, we get angular acceleration. Then, of course, we can find the moment of inertia of the wheel. So let's. I think I'll use this to find the angular acceleration. Or tangential acceleration equal to V final minus V initial divided by delta t. So in this case, V final is 2.25 minus 0 divided by in a time of 3 seconds, yes? Okay, so tangential acceleration equals to 2.25 divided by 3 seconds, we get 0.75. So tangential acceleration is 0.75, but remember, this is meter per second squared. We don't want tangential, we want angular. So how do you find angular acceleration? Of course, angular acceleration equals to, tell me the equation for angular acceleration. Equal to tangential acceleration, yes, divided by the radius. Excellent. So we can say 0.75 divided by the radius. What is the radius? The radius is 0.5 meter, yeah? So divided by 0.5 meters. So 0.75 divided by 0.5, the answer will be 1.5 radian. So 1.5 radian per second squared. So we've converted tangential into angular acceleration. Now, so we have this. What about this one here? We know that force and distance is given. So for the torque equals to force times distance, and then equals to moment of inertia multiplied by the angular acceleration. So this is what we need to find. We'll divide both sides by angular acceleration, or we can just say angular or moment of inertia, all right, equals to force times distance over this. You agree, yes? The force that we're using is 40 Newton multiplied by the distance. What is the distance? It is 0.15 divided by 1.5. All right, so 40 multiplied by 0.15, that is 6 divided by 1.5, that is equal to 4. So moment of inertia equal to 4. For what? What is the moment of inertia? That is, of course, kilogram meter squared. And that is how you would do it. So you write the information. First, you can find the tangential acceleration, then convert it to angular acceleration. That is the second step. And then third step, find the moment of inertia, which is 4 kilogram meter per second squared. All right, so far so good, yes? I hope, inshallah. Now we have another question here. It says, 2 uniformly solid cylinders. So we have 2 cylinders that are solid and uniform, of equal radii, so they have the same radius, roll down an incline without slipping. Without slipping, that means, of course, they have the net torque, you can say, or moment of inertia. Okay. The first cylinder has twice the mass of the second cylinder. This is very important. So the first cylinder has twice the mass. Oh, it's not writing. So the first cylinder okay, first cylinder has twice the mass of the second cylinder. How much torque was exerted on the first cylinder compared with the amount exerted on the second cylinder? So there is something you need to know. We can say, of course, R1 equals to R2. Why? Because they have the same radius. Now, in terms of the net torque, remember, we know that torque equal to, you can say, force times the distance. That's one way. If not, because we have mass in here, so we can say mg times the distance here, of course, that'll be the radius. So mg times the radius. But don't forget, yes? One of the masses, you can see the relationship between the torque and the mass. We can say the torque is directly proportional to the mass. And also, of course, directly proportional to the radius as well. So since they have the same radius, so there is no effect for the radius, okay, on the torque on this because they have the same radius. But in terms of the mass of the first cylinder is twice the mass of the second cylinder. So can we say that? So we can, of course, we can say m1 equals to 2 times m2. If that is the case, m1 is twice the mass of m2. So can we say the torque torque 1 will be twice as big as the torque on the second cylinder? And of course, that'll be correct, or solid cylinder, yes? So we can say the torque of cylinder 1 will be 2 times the torque that is exerted on cylinder 2. Why? Because the mass of cylinder 1 is 2 times bigger than the mass of the first cylinder. So 2 times bigger, that means the torque of 1 will be 2 times bigger than the torque of the second cylinder. So, but the question says the torque on the second cylinder compared to the first, yeah? So both sides divide by 2, or just take 2 under T1 in this case, or torque, let's say net torque 1. So we can say T2 or torque 2 would be, divide both sides by this, equal to half of the torque on, let's say, 1. So we can say the torque on cylinder 2 will be half of the torque on cylinder 1. But don't forget, what if they say compare the torques? Again, the torque on cylinder 1 is 2 times bigger than the torque on cylinder 2. But the torque on cylinder 2 is half of the torque on the first cylinder. All right, I hope this was clear enough. And the reason why, because the torque is directly proportional to the mass. Okay, now we have another question, of course, that is chapter review question. It says a 30 kilogram uniform solid cylinder. Whenever it says solid cylinder, don't forget, solid cylinder has a moment of inertia of 1/2, yes, because it is solid and it is a cylinder. So solid cylinder has a radius of 0.180 meter. If the cylinder accelerates at 2.3 times 10 to the power -2 radian per second square as it rotates about an axis through its center. How large is the torque acting on the cylinder? So find what? Find the torque acting on the cylinder. So let's see if you can find it yourself. So, like always, write the information that is given, or you can underline the keywords first, and then of course you can write the information that is given based on what you underline. So the first thing that we have a mass. The mass is, what is the mass? It is 30 kilogram, okay? 30 kilogram. Okay, it says what? A solid cylinder. So we have a solid cylinder, you can say. Okay, that's not a solid cylinder, but something like this. All right, something like this. Okay, so the moment of inertia for solid cylinder, you can say it is 1/2 mr squared. Okay, now just keep in mind. And then what else do we have? It says we have a radius of, so what is the radius? The radius is 0.180 meter. The next thing that we have, it says accelerates. So we have, is it angular or tangential acceleration? Look at the unit, yeah? The unit says radian per second squared. That means it is angular acceleration, which is 2.30 times 10 to the power -2 radian or watt per second square, radian per second square, as it rotates about the axis of rotation or through its center. How large the torque acting on the cylinder? So find what? Find the torque acting on the cylinder. So take a look. What are the information that you have? You have angular acceleration, you have mass and radius where you can find moment of inertia, right? And then of course you can find the torque. Okay, so to find the torque, we can say torque equals to moment of inertia multiplied by, or let's just say multiplied by the angular acceleration, correct? Yes. You do have the angular acceleration, so all you have to find this, then multiply these two together, you'll find the torque on the solid cylinder. So solid cylinder, once again, we're going to use 1 over 2 mr squared. So in one step, we can say the torque equal to 1 over 2 multiplied by the mass, multiplied by the radius squared, and then multiplied by the angular acceleration, yes? Okay, now plug in the numbers and then get it done. So 1 over 2, that is, you can say 1 over 2 or 0.5. This is the same, multiplied by, what is the mass? The mass is 30 kilogram, multiplied by, what is the radius? The radius is 0.18, 0.180. Don't forget, this is squared, okay? And then multiplied by the angular acceleration, which is 2.30 multiplied by 10 to the power negative 2. Now, use your calculator to find the answer for this. Half of 30, that is 15, multiplied by 0.180 squared, multiplied by 2.30 times 10 to the power negative 2, and the answer will be 0.011 whatever, or you could just say we can use a negative power of 10, which in this case, well, let me just write this one, 0.01117, or we can round it, make it 2 here. And of course this one, if you want to write power of 10, move this one 2 times, 1, 2. So it's going to be 1.12 times 10 to the power negative 2. Since it is the net torque, of course, it is Newton meter. And this is the final answer. Okay, here you go. Now, moving on. We have another question, that is question 23. Take a look. It's also interesting. But you need to know these very well. Okay, we have, it says, a 350 merry-go-round in the shape of a horizontal disc with a radius of 1.5 meters set in motion by wrapping a rope. As you can see here, so we have a merry-go. So there's a rope that is rounded, okay? So as you can see here, there's this rope. Once you pull the rope, of course, you can set the merry-go-round into motion. It says about the rim of a disc, yes? So you have shape of a disc pulling on the rope. How large a torque would be to have, or to, let's say, to be exerted to bring the merry-go-round from rest. What does it mean from rest? That means initial angular speed is 0 to an angular speed of 3.14 radian per second in 2 seconds. I believe it's easy as well. So let's solve this question as well. So what do we have? Okay, so we have a merry-go. We're trying to use a rope. We're trying to pull or make the merry-go-round rotate. The mass of the merry-go is, what is the mass? The mass is 350 kilogram. That is the mass. Okay. And then shape of a disc. So we have a disc, let's say. And of course, the moment of inertia for a disc, of course, is going to be 1 over 2 mr squared. Yes? Okay. And then the radius is, what is the radius? It is 1.5 meter. That is the radius. The next thing is set in motion by wrap. Okay, about this on a rope. How large the torque would be. So find the torque. All right, how large it is. Okay, starting from rest, that means omega initial is 0. Omega final is to an angular speed of 3.14. That is radian per second. And then the delta t that we have is just 2.5 0.0 seconds. So take a look. We have initial, final, delta t. We can use all this to find what? To find angular acceleration. And then using the mass and radius, we can find the moment of inertia. And then, of course, we can find the net torque. Okay. So using this, we can say the net torque equals to moment of inertia multiplied by the angular acceleration. So if I want to do this in one step, open a bracket, 1/2 for disk, mass times radius squared, and then multiplied by the angular acceleration. Of course, for angular acceleration, final minus initial, divided by delta t. Can you plug in the numbers and tell me the answer? Yes, well done. So let's get it done. Okay, so 1/2, that is 0.5, multiplied by the mass, which is 350 kilogram, multiplied by the radius, which is 1.5 squared. All right, and then equals to this, or you could just multiply the whole thing. What is final? It is 3.14. Initial was 0, so we could just say multiply by 3.14 divided by 2 seconds. And of course, the answer is 618.18, or we can say 618, or if I have another digit, I would go with 618.2 if I wanted. But I'll just go with 618, and that is because the net torque, of course, Newton meter. And this is the net torque on the merry-go, 618 Newton meter. Okay. Now, take a look at these Wrya questions. These are very important, and I hope you practice them. It says, I, in the equation, in this equation, it is called what? Of course, you can see that this is 2019 term 2 Wrya. Okay, question. So what does the I resemble here? Is it the angular momentum? What is the equation for angular momentum? That is not angular momentum, right? We're going to study next, inshallah. And then the intensity of a wave, that is not, okay, because we have net torque, okay, so there is a rotation. Is it the intensity of a current? Again, no, current is electricity, and this is mechanical rotational motion. And then moment of inertia, and of course the correct answer is moment of inertia, right? And that is option D. Which of the following equations are not true to find the torque? Okay, now so far we've been solving questions like this, or we've used this equation to solve questions. So we can, that means we can use this equation to find the torque. Yeah? What about this one? This could be possible, but let's take a look at the other questions, options, then we can get back to this. What about this? FD times, or F times d sine theta? This one is also can be used to find the net torque. So that means not this one as well. This one here, by the way, torque equal to I times delta omega over delta t. That is another equation for moment of inertia multiplied by the angular acceleration. So even this one can be used to find t. So the correct option, the only equation that can not be used to find the torque is option B, right? So this is the correct answer, which is not used to find the torque. Okay, now, it says, question 3 says, according, that is from 2021, okay, it says, according to Newton's second law, in the case of rotation, the angular acceleration of a body is directly proportional to what? The angular acceleration, don't forget. So we have angular acceleration, directly proportional to what? Is it directly proportional to the moment of inertia of the body? In order to do this, because it says Newton's second law of motion, yeah, why don't you write the equation of Newton's second law of motion for rotational, don't forget. For rotational, we know that, right? Net torque, let's write a nice one. All right, not very much, but moment of inertia times angular acceleration. So angular acceleration, we can say equals to the torque, or net torque, you can say, divided by omega. So now, whatever that is above the fraction is directly proportional. Yes, if it is something below the fraction, it means inversely proportional. So Newton's second law of motion, of a body, the angular acceleration of a body is directly proportional to what? Is it directly proportional to the moment of inertia? Is it directly proportional to the moment of inertia? Clearly not. Is it directly proportional to the result of the applied torque? Here's the applied torque, yes? So we can say yes, possible, but how about we take or we look at the other options as well. So this, keep an eye on this, okay? It says to a body's volume. Volume is, we can say it depends on, or the moment of inertia depends on the volume, because based on the volume, we will know whether if it is 1 over 2, whether if it is 1 over 12, let's say, or 3 over 2 over 5, 3 over 5. So volume would be related to the moment of inertia. So not C. What about D? The body mass. Again, mass would, the moment of inertia would depend on that. So the correct option would be option B in this case. All right. Now, moving on. Question 4 says, which of the following statement is correct? With a net positive torque. Now, do you remember what was net positive torque? We said the angular acceleration must increase. It says the angular acceleration of an object is clockwise. Is it? No, it has to be counterclockwise because it is positive, yes? Okay, now option B says with a net positive torque, if the torque is positive, the angular acceleration of an object is counterclockwise. So this is possible. Let's keep an eye on B, okay? Because it says positive and it says counterclockwise. All right, what about the other options? With a net negative, so if the torque is negative, the angular acceleration of an object is counterclockwise. No. If it is negative, it has to be clockwise. D says if the net force this time on the object, or the net force on the object is not related to translational acceleration given to the object. Based on translational object, we know that, or in translational object, F equal to mass times acceleration, yes? And that is, it says the net force on an object is not related to translational acceleration. This is an incorrect option, so the correct option is B. Again, with a net positive, that means the rotation is counterclockwise. All right, moving next. It says a 350 merry-go-round in a shape of a horizontal disc with a radius of 1.5 meter is set in motion by wrapping a rope around the rim of the disc and pulling on the rope. How large a torque would have to be exerted to bring the merry-go-round from rest to an angular speed of 3.14 in 2 seconds. In the previous question, of course, we've solved something very similar to this, so I would recommend you to go back to watch the previous video. If you don't know how to solve this one, then come back and solve question 5, which is very important for you. All right, now as for question 6, it says a force of magnitude 4 Newton applied tangentially to a disk of diameter of 0.2. If the angular acceleration of the disk is 8 radian per second squared, what is the mass of the disk? Yeah? Use this equation I, moment of inertia equal to 1 over 2m times radius squared. How about we do this question together? All right, let's do this. And then I would really rather you solve this question on your own and see if you can solve it yourself, and then compare the answer, see if you did it. That's not what I wanted. Okay, so let's go back to paint. All right, so it says what? A force of, so we have a force, it says tangential force, of what value? Of 4 Newton, yes. Okay, to a disk of diameter, so we have, that's very interesting. In the previous questions, we used to have radius, but here, what do we have? We have diameter, okay? So how do you convert diameter to radius, guys? So we know that radius equal to diameter divided by, or let's use capital D for diameter. Diameter divided by 2. So what is the diameter? The diameter is 0.2 meter divided by 2, of course. That means the radius is going to be 0.1 meter. Okay, that was very good. If the angular acceleration, so we have angular acceleration, which is 8 radian per second squared. Okay, what is the mass of the disk? So find the mass of the disk using that equation. So take a look. We have, let me draw this. We have a disk. So there is a force. You can say if the force is applied tangentially, that would be tangent to the circle. And of course, we have a radius. So this causes a torque force, and radius causes a torque. This torque would rotate the disk. But remember, the disk would have a moment of inertia. We'll use this equation to find what? To find the mass of the disk. All right, so bear with me. Let's solve this. So we'll say net torque equals to moment of inertia times angular acceleration. Once a force is acting on it, of course, it starts to accelerate if the force is big enough. So, but for this one here, of course, we have Ft times the radius is equal to, because it is a disk and the question itself gives you this equation, so we'll use 1 over 2 mass times radius squared, and then multiply by the angular acceleration, which is, of course, what is the angular acceleration? It is 8 radian per second. So what are we trying to find? We're trying to find the mass, this, okay? Now plug in the numbers and let's find this, yeah? So the force that is applied is 4 Newton multiplied by radius. What is the radius? It's 0.1 meter. We don't need the meter for now. Okay, equal to 1 over 2. The mass is unknown. What is the radius? By the way, the radius of the disk is 0.1 again. So we can say 0.1 squared and then multiplied by 8. Okay, so 4 times 0.1, that is 0.4. Okay, and then this 2, that is going to be 4. Half of 8, 4. 4 times 0.1 squared. So 4 times 0.1 squared, that is of course equal to equal to what? Equal to mass times, or let's just say 0. Let me go back to this. 0.04 times the mass. Okay. All right. Now, how do you find the mass? Mass equals to 0.4 divided by 0.04, and of course the answer here, 0.4 divided by 0.04, the answer will be what? Will be 10. 10 what? 10 kilogram. And this is the mass of the disk. Okay, so 10 kilogram. Let's see if we have 10 as an option here. Which one was this? Okay, it was this one. Yes, of course the answer is D. The answer is, okay, let's get it back. Let me change the color as well. So the answer is D. Now you try, see if you can solve question 7, yes? And in terms of question 8, the potter's wheel has a shape of a disc and a radius of this. The mass is this much, revolving or rotating, let's say, at a 50 rev per minute. Don't forget, this rev per minute has to be converted to radian per minute, multiplied by 2 pi, each minute equal to 60 seconds, yeah? So 50 times 2 pi over 60 seconds, the potter can stop the wheel, right, in 6 seconds by pressing a wet rag against the rim. How much torque does the potter applies on the wheel? Now, for this one here, I would rather you try this. We've solved a question similar to this in the previous questions that we have solved in this session. So you try to see if you can get the answer, yeah? And of course, the answer for this question will be negative 11 Newton meter. If you tried this and you didn't get negative 11 Newton meter, then watch the previous questions that I have solved. You will see a question very similar to this, and then get back to this and try it again, hoping to get negative 11 Newton per meter. Until next lesson, please keep practicing, and if you have any questions, I would always recommend you to write it down in the comment section or comment section below. So till then, stay safe and keep practicing. Assalamu alaikum wa rahmatullah.